Gravity is one of the four fundamental forces of nature. It is the force of attraction that exists between any two objects that have mass. The strength of gravitational attraction depends on the mass of the objects involved. The more massive an object is, the stronger its gravitational pull becomes. On Earth, gravity is what keeps us grounded and causes objects to fall toward the ground. It also governs the orbit of the moon and artificial satellites around our planet. Gravity is not just an Earth phenomenon. It operates throughout the entire universe, holding planets in orbit around stars and keeping galaxies together across vast distances of space. Newton's law of universal gravitation describes this force mathematically. The formula states that the gravitational force equals g times mass 1 times mass 2, divided by the distance squared. Let me explain each variable. F represents the gravitational force between the objects. G is the gravitational constant, a fundamental value in physics. M1 and M2 are the masses of the two objects, and R is the distance between their centers. This Newton's cradle demonstrates how gravitational effects transfer momentum and energy between objects, showing the fundamental principles of gravity in action. Gravity affects everything around us in ways we can observe every day. One of the most familiar examples is watching an apple fall from a tree. When the apple detaches from the branch, Earth's gravitational force pulls it downward at an acceleration of 9.8 meters per second squared. The moon's gravity creates another visible effect on Earth, ocean tides. The gravitational pull of the moon causes water to bulge toward it, creating high tides. The water on the side of Earth facing the moon experiences a stronger gravitational pull, while the water on the opposite side experiences a weaker pull, creating two tidal bulges. On a larger scale, gravity keeps planets in orbit around the sun. The sun's massive gravitational field provides the centripetal force needed to keep planets moving in their elliptical paths. Without gravity, planets would fly off in straight lines. The gravitational attraction between the sun and planets creates the stable orbital motion we observe. It's important to understand that weight and mass are different. Mass is the amount of matter in an object, while weight is the gravitational force acting on that mass. The formula for weight is mass times gravitational acceleration. On Earth, this is your mass multiplied by 9.8 meters per second squared. Gravity is not exactly the same everywhere on Earth. It varies slightly due to altitude and the density of rock beneath the surface. At higher altitudes, you are farther from Earth's center, so gravity is slightly weaker. Dense rock formations can also create stronger gravitational fields in certain areas. Astronauts in space experience what we call microgravity. This is not the absence of gravity, but rather a state of continuous freefall around Earth. The space station and everything inside it are falling toward Earth at the same rate, creating the sensation of weightlessness. Gravity is still present, but its effects are not felt. Newton's cradle demonstrates how gravitational potential energy converts to kinetic energy and transfers momentum through collisions, showing gravity's role in energy transfer. When we lift and release the first ball, gravity pulls it down, converting potential energy to kinetic energy. The collision transfers this energy through the stationary balls.